So, if it is an elastic, we generally use a simple modulus function, and if it is a time dependent functions, you have also been introduced to a relaxation modulus or a creep compliance functions. Now, in the oscillatory shearing, we use a modulus called as a dynamic modulus. Maybe you are new to this term, but you will understand what is dynamic modulus, and phase angle you already know what is delta. In case of a strain control test, and creep compliance function and modulus in case of a stress control test. We will see how to determine these modulus functions when we are subjecting the material to an oscillatory shearing. So, we have assumed the response of a material to be linear. So, to define a material functions, we will use a Boltzmann superposition principle. So, as a material exhibits a linear response, Boltzmann superposition principle for a stress response, let us use a strain control test here. So, for a strain control test, when we apply a sinusoidal loading for a Boltzmann superposition, integral form of a Boltzmann superposition as given in this equation, we will get the response stress to be this. So, this is the same integral form. If you put S as t minus t dash, you will get this expression. So, when you look into this expression, G s is some material function equivalent to a modulus, and omega is a frequency as defined earlier, and gamma naught is a strain amplitude. You get this function by substituting gamma dot of t to be gamma naught omega cos omega t. So, when you substitute this in the Boltzmann superposition, the equation simplifies to this. Now, you can expand this equation for cos maybe omega t minus omega s to be equal to, let me write it here, cos omega t minus s, this is equal to cos omega t cos omega s plus sin omega t sin omega s. So, when you expand this term cos term, the equation simplifies to this. Now, when you closely look into these expressions, the response stress function has a two component, one is a sine component and other is a cos component. So, the coefficient of sine component, again it is a function of frequency, and the coefficient of cos component is a function of frequency. So, our input strain function is sinusoidal, only it has a sine function which is gamma is equal to gamma naught sin omega t. So, we control the strain in the sin omega t pattern in the sine waveform. Our stress waveform has both sine as well as a cos waveform. So, one is in phase component with an input, another is an out of phase component with an input. So, this in phase component with an input or the coefficient of term sin omega t, we call it as a elastic modulus. Or it is a elastic response, so or otherwise storage modulus, and it is generally represented by G prime. And the coefficient of cos omega t, which is an out of phase component with a strain, we call it as a loss modulus or viscous modulus. Viscous modulus or loss modulus, and we represent using a term G double prime. So, you have two functions here, One is an in phase component storage modulus and other out of phase component loss modulus. So, if you want to find a stress, you need a two function storage modulus component and the loss modulus component. You can also see that these modulus functions are a frequency dependent. So, now the next question is, are these storage modulus and loss modulus independent functions or it is related to each other? See, these functions are not an independent functions, they are related to each other, they are not an independent function. They are related to each other. So, you need these two functions to define a stress waveform. So, stress waveform in simple can be written as the equation given here in terms of storage modulus and loss modulus. So, now let us summarize the storage modulus loss modulus equations that we saw before. So, tau of t can be written as gamma naught, which is strain amplitude, into g prime sin omega t. Sin omega t coefficient is g prime, cos omega t coefficient is g double prime. We have assumed viscoelastic material exhibits a stress of the form tau naught sin omega t plus delta. Now, we will find a relation between g prime, g double prime and a phase angle now. So, you can expand this function. When you expand this, we will get tau of t to be tau naught cos delta sin omega t plus tau naught sin delta cos omega t. So, comparing an equation, suppose if this is A and this is B, you can equate the coefficient of sin omega t term. When you equate the coefficient of sin omega t, you will get gamma naught g prime to be equal to tau naught cos delta or g prime to be equal to tau naught by gamma naught modulus function into cos delta. So, loss storage modulus and phase angle are related with this expression. Likewise, when you equate the cos omega t coefficient, you will get gamma naught g double prime to be equal to tau naught sin delta, or otherwise g double prime will be equal to tau naught by gamma naught into sin delta. So, storage modulus and loss modulus are related to phase angle, both one is a sine function and other is a cos functions. So, one way of representing material functions for a linear viscoelastic behavior, or when we subject the material to an oscillatory shearing, is either using a g prime and a g double prime value, and both this g prime g double prime are related, and you can get the relation between this using a phase angle function. So, in another way of representation is using a complex number. We define this complex number as a complex modulus. We have a real part of a complex number. We use that real part for representing an elastic modulus. Imaginary part, which represents the loss, we use it for giving a loss modulus. Now, if you see a complex number, a real part represents the elastic modulus and the imaginary part represents the loss modulus. So, the mod of the complex number is what we get it as a dynamic modulus, and you can determine using this expressions. G prime is related to cos delta and g double prime is related to sin delta. So, the ratio storage modulus, loss modulus to storage modulus is a tan delta. So, if you want to determine a phase angle from a storage modulus and loss modulus, you can use this expression. We can also represent in the vectorial form the storage modulus and loss modulus as, this is a dynamic modulus. If it is delta, when the delta value is 0, we will get a storage modulus, and the delta value is maximum, we get a 90 degree here. When it is maximum, you will get a loss modulus. Now, next we will define a creep compliant functions for the stress control test. So, for this we will directly use the way in which we defined the dynamic modulus. We will use that concept and we will define a creep compliance functions for this. So, in the stress control test, we control the stress in a sinusoidal pattern, and the response strain will also be sinusoidal with a lag. This is a ideal viscoelastic material behavior. So, this is the response function. For this response function, with the stress to be sin omega t, again the strain will be a function of sin and a cos omega t. If you expand this, and if you proceed in the same way as we proceeded for the dynamic modulus function, you will get this function to be a real part function to be like, you can separate this with a coefficient of sin term and a coefficient for a cos term, and you will get two modulus, one corresponding to a elastic response. We will use the term here J for defining a creep compliance. So, this creep compliance will have two component. One is a real part which represents the elastic compliance, and other is an imaginary part which represents the viscous or a loss compliance. So, the mod of a creep compliance function is used in defining the material functions. So, similarly, you will, as you did it for a dynamic modulus, you will get a delta value to be tan inverse of viscous compliance by elastic compliance. So, this is in case a stress control test. So, let us quickly recollect what we saw for a stress control test and a strain control test in an oscillatory mode, and then we will see whether we have defined a material function. We will see whether these material functions which we defined for the stress control and a strain control test are related to each other. So, in a strain control test, we controlled the strain and measured the stress, and the stress for the viscoelastic response is given by tau naught sin omega t plus delta. We defined a modulus here, and the modulus is called as a complex modulus. This modulus can also be determined from the ratio of tau of t to gamma. Likewise, this is also a function of time. Input is also a function of time. So, tau of t by gamma of t. Likewise, in a stress control test, we controlled stress in a sinusoidal pattern, and the stress strain response for the sinusoidal strain for a viscoelastic material will be gamma naught sin omega t plus delta, minus delta. So, we defined a function called as a creep compliance, complex creep compliance, which is defined as gamma naught of t divided by tau of t. Now, if you use this tau function and gamma dot function in the complex creep compliance, and this gamma and tau in this dynamic modulus creep compliance, and compare both these two equations, you can prove that the product of the complex modulus and the complex creep compliance is 1. you can also prove that a product of dynamic modulus and the mod of complex creep compliance, we call it as just a creep compliance, to be again 1. So, if you need more clarifications on this, how to derive, please contact us. So, we have seen how to we have seen different material functions that we used to quantify that we used to define the viscoelastic behavior when you test it under a oscillatory shearing. Now, we will calculate the energy dissipation of a material when it is subjected to an oscillatory shear. So, energy dissipation in a material can be defined using this work done equation. So, the equation here is per unit volume. So, you have an integral equations as a function of stress and the strain rate. Now, if you solve this integral equations for a controlled strain, sinusoidal strain or a sinusoidal stress, you will get the function to be this is for a strain control test. If you conduct a stress control test, you will get this equation in terms of J double prime. So, just a simple way to solve this is use a t value which is one waveform, time taken to complete one waveform. So, it is 2 pi by omega. Use a t value to be 2 pi by omega with a strain control test, tau dot is gamma dot is gamma naught cos gamma naught omega cos omega t, and tau of t for a viscoelastic response is tau naught sin omega t plus delta. When you substitute both these expressions in the first equation here, you will get a energy dissipation per unit volume in a material to be related to a stress amplitude tau naught, strain amplitude gamma naught and phase angle delta. And we already know that this sin delta is related to loss modulus by the function loss modulus equal to sin delta into stress amplitude by strain amplitude. So, using this relation, if you replace the sin delta value, you will get the energy dissipation in terms of a loss modulus. So, this energy dissipation equation is used in a bitumen testing in performance grading of binder. So, based on the energy dissipation, you can say when the payment or when the binder starts rutting or when the binder starts cracking. So, this is as energy dissipation varies with the temperature. So, you can find the energy dissipation values at a different temperature by defining the tolerance limit. You can say that when the dissipation exceeds the particular value, the payment fails in rutting, or when the dissipation exceeds extreme values in a low temperature, you can say that the payment fails in fatigue cracking. Next is a constitutive modeling. We have seen a response of a material to an oscillatory shearing, and we have defined a modulus functions and a phase angle functions for the an oscillatory shearing. Now, we will see how to predict the response of a material to an oscillatory shearing using a simple linear equations. So, these constitutive model equations are a one dimensional equations. We will focus here with a normal Maxwell model. You have been already introduced to this Maxwell model, Kelvin model, and Burger's model. You have been already introduced to these Maxwell, Kelvin and a Burger model. So, we will directly use the constitutive relations and substitute the stress strain waveform functions in this and see what will be the response of these functions, these equations. So, the differential form of a Maxwell model can be written as in these equations. So, the shear stress and the derivative of a shear stress here, and gamma dot function here. Here Maxwell model, as you know, can be visualized as a combination of a spring or elastic component and a viscous component in series. Now, if I define the material functions, viscous material function as eta and the elastic function as g, so the relaxation time gamma can be given by eta by g. So, the rate type equation for the Maxwell model is as given in this expression. So, let us use this expression constitutive relations to solve the tau function, tau of t expression for a controlled strain input of omega t equal to gamma naught sin omega t. So, we know strain to be gamma naught sin omega t. So, if you substitute the strain function in this constitutive relation and solve for tau, you will get the relation of tau to be of these form. Now, if you closely look into this relations, again this equation has a sin omega t cos omega t term. So, the control response, which is strain, is gamma naught sin omega t, and the stress response is a function of sin and cos term. So, again here if you look into this, you have coefficient of sin term and coefficient of cos term. You know, we defined the coefficient of sin term to be a storage modulus. So, storage modulus here, which is gamma naught g omega square lambda square divided by 1 plus omega square lambda square. Likewise, loss modulus will be coefficient of cos omega t, which is gamma naught into g omega lambda divided by 1 plus omega square lambda square. So, we have storage modulus and loss modulus for a Maxwell model. If you see, these modulus are frequency dependent. Now, phase angle will be tan inverse of g double prime by g prime. So, you can put a tan inverse of g prime by g double prime, you will get the phase angle or a tan delta to be a function of frequency. So, you have a frequency is also here a time scale, and lambda here is also a time scale. So, you should know that frequency time scale is an experimental time scale, and the lambda or a relaxation time is a material response time scale. So, here we see that the storage modulus and the loss modulus is a function of frequency, and the ratio of a storage loss modulus to storage modulus gives a tan delta value, and the tan delta value is linearly, it increases with, it changes with again a frequency. So, this is how the trend is as you test it across different frequency. So, the modulus value increases as the frequency is increasing. So, you can see the increasing trend of a storage modulus here, it consistently increases and reach a steady value when you test it at high frequency. In case of a loss modulus, as the frequency increases, you can see a increasing value initially, and then as the frequency increase further, you can see a decreasing functions. Tan delta value, you know, as this tan delta is related to a frequency inverse of frequency as 1 by omega into gamma. So, you will get the tan delta function to be related to the inverse of frequency. So, this is a critical Maxwell model response when you subject the material to an oscillatory shearing. So, if the material behaves as a Maxwell model, the storage modulus, loss modulus and tan delta will vary something like this. So, next is a Kelvin model. we have a differential equation of a differential form of constitutive relation here for a Kelvin model. So, tau depends on strain and strain rate. So, Kelvin model can be physically viewed as a spring connected by a dashpot in series. So, with a constant spring constant to be g and a dashpot constant to be eta. So, when you solve these equations for again gamma dot to be gamma naught omega cos omega t, substitute and gamma to be gamma naught sin omega t, it is just a mere substitution. When you substitute in these expressions, you will get tau to be of this form. Again you will have two functions, one is sin omega t function, another is a cos omega t functions. So, the coefficient of sin omega t, you can see that it is independent of frequency, it is independent of frequency, and the cos omega t coefficient, which is a loss modulus, is linearly related to a frequency, and tan delta, which is nothing but gamma naught eta omega by gamma naught g is linearly again varies with the frequency. Gamma by g is a relaxation time. So, tan delta can be represented as a product of relaxation time and a frequency. So, storage modulus, we cannot define it for a different frequency. Loss modulus varies linearly with the frequency, and tan delta is a linear variation again with the frequency. This will be a typical response of a Kelvin model. Now, Burger's model, 4 parameter model, let us start from this constitutive relations. So, now if you solve this constitutive relation for a strain input of gamma naught sin omega t, you will get the response function to be this. Let us use the term here. So, this is a complex modulus, real part of the complex modulus and imaginary part of a complex modulus. So, we have this portion function to be a storage modulus and this function to be a loss modulus. So, this storage modulus term and the loss modulus term depends on frequency. For this constants P1, P2, P3, you can refer this. So, when you look into the response function of a Burger's model over a wide range of frequency, so you have a frequency scale here, it is in the logarithmic scale. This values or this curve is obtained for a R1 value, R2, eta 1, eta 2 value for a fixed values. So, R1 is 10 power 10 dynes per centimeter square, and R2 is 10 power 5 dynes per centimeter square, and eta 1 is both eta 1 and eta 2 in a poise, again 10 power 5 and 10 power 5 poise. So, R2 is 10 power 5. So, this is, if you see the variation in the modulus across the frequency, across a wide range of frequency, you can see that the storage modulus, it is a logarithmic of a storage modulus, the storage modulus increases with the frequency, and when it reaches a value near R2 value, it was constant for some period of time, so for some frequency, and then it started increasing, and asymptotically it reached a constant when the value reached, when the modulus value reached the value of R1, which is R1 is spring constant here, spring constant in the Maxwell portions. So, the variation in the loss modulus is something which is given in this curve. Initially there is an increase, and after when a further increase in the frequency, you can note a decrease in the modulus. So, this again trend depends on the material functions R1, R2, eta 1 and eta 2. So, we have seen constitutive models are the behavior of various models that includes a Maxwell model, Kelvin models and the Burger's model. Next, we will see few experimental investigations that we conducted for a bitumen in an oscillatory shear mode, and we will discuss the results of the bitumen and we will see which model suits the bitumen behavior. Let us see it in the next part of our lecture. Thank you.